Well, I guess there's a portable board around here somewhere.
That's from an old German word.
I'm
Like,
trying to get one of those.
only the U.S. and the U.S. and Germany and the U.K. are the only places that call it Easter. Everywhere else calls it Passover or some form
Oh.
of Pascha, which is the Greek word for Passover.
Oh, okay. Interesting. Okay. So, continuing the householder matrices. The QR factorization. So where I left off was just explaining what is a householder matrix and the fact that it is symmetric and orthogonal. So, identity minus 2. I'm going to simplify the definition a little bit here. 2 VV transpose, where V is required to be a unit vector. Because last time I had UU transpose over U transpose U, where U could be any vector, non-zero vector, but if we make it a unit vector, then we can stick with this. So how can we use P to zero out elements? That's what we really want, because for QR factorization, we want to multiply A by orthogonal matrices on the left to zero out elements below the diagonal, like in Gaussian elimination. So what I'll do is, given a vector x, we want to find V to use in this definition of household reflection, so that Px is equal to some multiple of E1, the first standard basis vector. So in other words, we're going to zero out all elements of X except for the first one. And because P is an orthogonal matrix, that tells us pretty much what alpha has to be. Alpha must be plus or minus the 2 norm of X, because multiplying any vector by an orthogonal matrix has to preserve the 2 norm. Okay. Now, the way we'll do this is, so we just need to find the magic V that will make this happen. So Px is equal to its identity minus 2 V transpose X. And this is a good time to show how we efficiently multiply by a householder reflection, because you don't actually, just as one of the commandments of numerical linear algebra is you never ever ever explicitly compute the inverse, you never ever 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 explicitly form a householder reflection, the P here. Because if you look at how this product works, if you distribute the X, you get X minus 2V, and then this V transpose X, that's a dot product, V transpose X. So matrix vector multiplication normally takes order n squared operations. But here, this is only going to take order n, because the inner product will take order n, and then you're subtracting 2 vectors, that's also order n. So there's no reason to ever explicitly form P because of its nice structure, and the fact that we have this outer product when multiplying by a vector just gives you an inner product. So we're going to use this to try to figure out what V should be in order to have most of the entries of a result equal to 0. So I'm going to set this equal to alpha E1. And now I'm just going to rearrange this. So move this to the other side, move this to the other side. So I have X minus alpha E1 is equal to 2V. Well, I'll rearrange this too. Because V transpose X, that's a number. I can put that wherever I want. And then we have V. All right. Well, in fact, I can. Well, actually, I'll just leave it like this. Okay. Now, the key here is the right side is just some multiple of a vector V that we want. And we know V has to be a unit vector. So this multiple of V must be equal to this. So that means, but V is required to be a unit vector. So all we have to do is set V equal to this vector normalized. Because that satisfies the two requirements that we have on V. One, it must be a unit vector. Second, it must be parallel to this vector. So that completely determines V up to plus or minus. And in fact, plus or minus ends up not mattering. In the depth, we get the same P, because if I take this P here, well actually, this one, and I replace V with minus V, because it appears twice, the minuses will cancel out. So now we have our magic V. But now I want to show you what it is like on the element by element level. Now alpha is plus or minus the 2 norm of x, but we'll settle the plus or minus in a little bit. For now we just know that we have some constant alpha, we know what it is. So, so we look at this vector equation on a element by element level. So the first element, V1, is going to, okay, so first element of this is going to be x1 minus alpha. And then down below, if I were to write out this inner product, well, using this identity, the norm of a difference of vectors squared is norm of u squared minus 2 inner products of u and v plus 2 norm of v squared. So if I apply that with u equal to x, and then v is equal to alpha e1, that's going to give me norm of x squared minus 2, and then the inner product of x with alpha e1, e1 is just going to pick off the first element. So it's 2 alpha x1, and then the 2 norm of this will be alpha squared. Okay. But the thing is, alpha is plus or minus the 2 norm of x. So I can simplify this. It's going to be 2, so this is going to be alpha squared, and I have alpha squared over here. So I have 2 alpha squared minus 2 alpha x1. And in fact, well, actually, I can go ahead and factor out 2 alpha minus x1. So now, depending on whether alpha is actually, let's do it like this. Okay. So now I can cancel these out, kind of. Well, I just have to be careful about the sign of alpha. So for instance, suppose alpha is positive, then this had better be positive also, and then and therefore this would be positive, and then I can go ahead and cancel it out as this. But if alpha is negative, then this had better be negative. And that's going to introduce, and then canceling, because I assume by default that square roots are positive square root, that's going to introduce another minus sign. So what I actually have here, if I simplify it as much as I can, is minus, and then I have the sign of alpha, so 1 if it's positive, minus 1 if it's negative. And then I have square root of alpha minus x1 over 2 alpha. So this is the simplest form I can get for the first element of V. And then all the other elements are going to have a very similar form to each other. So V2, for instance, I'm going to have just x2 up top because I'm subtracting off alpha E1. All other components of alpha E1 are going to be 0. So I'm just going to have x2 over, and then the denominator is going to be exactly the same. So I'd have like 2 alpha minus x1. So then what I can do is, okay, 2 alpha. Is I can work this expression into it. This ends up being the same as minus x2 over 2 alpha v1. Okay. Because what I can do is, if I were to take this and multiply by, or multiply and divide by 2 alpha, then you can see how I arrive at this. And then similarly for all the other components, vi is xi over 2 alpha v1. So so this gives me a quick and easy way to compute all the components of v, just using this formula that I boxed here, and then this other formula that I also boxed for I greater than 1.
So the V on the bottom is always 1, or is it VI?
This one is v1.
That one's V1.
Yeah. So
And
what?
it's XI on the top.
Right.
Okay, got it.
Yeah. So once I compute the first component, that gives me a quick way sub-expression for all the other components.
Okay. I was thinking it was I minus 1, like the previous V.
Oh,
It's
yeah,
not.
yeah. That's why I gave a general pattern down here.
Got
Yeah,
it.
yeah.
Okay. It's just V.
Mm-hmm. Oh, dang it! That minus is also supposed to be there.
Okay.
Okay. So questions about how these were arrived at. Okay. Now, the only thing I haven't cleared up is alpha is plus or minus the 2 norm of x, but which one should it be? So this expression tells us which one to use. So choose alpha to have the opposite sign of x1. Why is that the better choice of the two? Because we would end up zeroing out these elements of x no matter what, no matter which positive or negative alpha we chose. But why is this one better?
Because that will cancel out with that minus sign, and you'll get positive.
If it's negative.
Yeah, the numerator could still end up being positive or negative. But it actually has to do with floating point arithmetic.
Does it avoid cancellation?
Yes, so bad subtraction. Yeah, so that way the numbers you're adding will always be of the same sign when you have x1 and then minus alpha. So yeah, you avoid the risk of catastrophic cancellation this way. Okay. Now. All right. Okay, actually, yeah, to be a little clear of what I was getting at before, since alpha and alpha minus x1 have to have the same sign to ensure square root of a positive number. Therefore, this will also have that same sign underneath. But because alpha minus x1 is out here by itself, it could be positive or negative. But once we get rid of it by simplifying with this, we still have to make sure that sign is positive or negative is still represented, and that's why that sign function has to go there. Now, one little wrinkle to keep in mind is, let's suppose that we choose alpha to be positive. So it's a positive 2 norm of x. So if alpha is greater than 0, can anyone tell me, why is it guaranteed that alpha minus x1 is also going to be positive? Now, if x1 is negative, that would definitely assure that. But let's suppose x1 is positive. So you might think, well, what if x1 is so big that this turns out to be negative? How come that absolutely cannot happen?
Because alpha is the 2 norm of x.
Yes. And let's take a look at that. It does, yeah, it's because of that. But let's drill down to details here. So 2 norm of x, okay. Is that really greater than, I'll square both sides. Because what is this? If I write this out on the element by element level.
It's just the sum of all the individual, like the elements.
Yeah, including x1 squared plus all the other stuff. Yeah, so, well, at least we could say it's greater than or equal to. Yeah. But again, if that was the only element, we wouldn't have to zero anything out. So, yeah, for an interesting case, yeah, it has to be strictly greater than. So, yeah, we don't have to worry about something going wrong there. All right, so it's one of those little subtleties. Okay. All right, now. All right, so now we have a way to construct a household reflection to be nice and destructive, like we need it to be. That can zero out elements. So the way we can, so now I can describe how to use household reflections to compute a QR factorization. And I think actually do not have the algorithm in the notes. Or I might have it in a different part of the notes, but I want you guys to see it anyway. Okay. Okay. So for this, I'm going to introduce first a helper function. A function that is called house x. So in other words, what this function does is, so it takes as input a vector x, produces output a vector v, And this is the unit vector v, so that p x, which is identity minus 2v transpose x, is equal to alpha e1. So everything I just described about how you get that vector v that will cause x to be mostly zeroed out, that little helper function is going to do it for us. Okay. So way this works is as in Gibbons QR, also Gauss elimination, we go column by column, starting from first column. Well, I actually need some initializations, like with Gibbons QR. First, I'll set R equal to A, and Q equal to the identity matrix. So I'll loop over all the columns from 1 to n, so using my MATLAB syntax there. And I get my householder vector v, but I have to pass the right part of R, which is originally my A, in order to get it. So first I'm going to be working on the first column. So the first time through, I want to pass the first column, because I want to zero everything below the diagonal. So that's everything except the first element. But then I'm going to move to the second column. And I want to zero everything in the second column again below the diagonal, so everything except the first two elements. So in other words, I want to have householder transformations that affect less and less as I go from left to right through a matrix. So I'm going to pass in R, and I want not the entire column. The first time around, I want the entire column. Then I want to keep taking less and less. So it would be elements, so rows J through M, this is an M by N matrix, and then column J. So it's J, the column J from the diagonal to the bottom. So that's what I pass as my X, and then I get out my V. Okay, so this is the essential part of my householder reflection, and now I'm going to apply that householder reflection. So now what I do is I'm going to multiply by this householder reflection on the left. But again, I don't want to work with the whole matrix. For one thing, this householder reflection is only going to affect rows J through the bottom. And also, it's only going to affect columns from column J to the end. And the reason, now, technically it would affect all columns, but the thing is, to show what's happening in my matrix R that is originally A, so at first time around, when J is equal to 1, I'm going to pass this entire column as my X, and then I'm going to wipe out everything below the diagonal. And then I go to J equals 2, and I select this part of a column to be my X. And I want to work on just this portion of a matrix. I don't want to touch the first row anymore. So I'm working on this part, and specifically I want to zero out these elements. Now, I only need to multiply this matrix by my householder reflection affecting these rows. But I only need to touch, even though it would work on the first column also, this portion of the first column is already all 0. So there's no need to work on it. It would just become 0 all over again. So that's why I can only need to deal with columns J through the end. Okay. Now, when you're multiplying by householder reflection on the left, if I have identity minus 2v transpose R, that's the same as R minus 2v V transpose R. So I'm subtracting something from R itself, so I can just fill that in. Okay. And then what we have here is, this is a dot product, so this gives me, but I have a row vector with a matrix, so this is going to give me a row vector again. So I have column vector times a row vector, that is a outer product. So I have minus 2v, and then I have v transpose times that same portion of R that I'm working on. Okay. Now here's a MATLAB subtlety for you. It's actually very important from an efficiency point of view to put parentheses around this expression, because by default, MATLAB is going to multiply vectors and matrices from left to right. So if you don't put the parentheses, it would actually group those together. And what would happen in that case is it would form this outer product matrix and then do a matrix multiplication, full matrices, order n cubedville, and you don't want to go there. So instead, if you make it do this first, that forms a vector, this matrix vector multiplication, and then an outer product, which is quick. So you remain in order n squared land. So parentheses are very important for that reason. And so you still get the correct result either way, but you don't want to take that kind of time. All right. There's been cases where I have some MATLAB code, and I get an out-of-memory error. It's just basically we're working with a matrix that's just too big. And then I realized, oh, I did something kind of like that for getting in parentheses, and I just rearranged the grouping of the operations, and then it's fine. Okay. So that will take care of zeroing out the subdiagonal entries of R, eventually reducing it to upper triangular form. But the only other thing that's left is updating Q. And we saw this in Gibbons' case, where you apply the Gibbons rotation on the left to zero out your subdiagonal entries, and then you apply that same Gibbons rotation on the right to your Q to keep updating it. So I need to do that same kind of thing here. Now, when I'm applying a householder reflection on the right, so that would be Q minus 2Q times V transpose. Now, what's going to happen in this case is what I was doing with rows when applying to R is being done with columns when I'm applying to Q, just because it's happening on the opposite side. So the one thing to keep in mind is now, just as this householder reflection affects only these rows when you're multiplying on the left, it only affects those columns when applying on the right. So the columns J through M are what are going to be touched by this householder reflection. But the difference is I need to affect all rows. And the reason for that is in R, you're zeroing certain things out. Like I didn't need to work with this because it was all recombining zeros. That's not happening in Q. Q is a full matrix. Or it starts out identity, but eventually becomes a full matrix. So that's why I need to deal with all rows in this case. All right, so then I have QV, well, same portion of Q. Oh, this is J to, okay, sorry, Q is an M by M matrix, whereas R is M by N. Okay. And here the parentheses are not absolutely necessary, again, because we're associating from left to right, but just for uniformity, I'm putting in parentheses in anyway. And that's it. That is your QR factorization by householder reflections. Now, still takes order n cubed operations because each of these matrix multiplications takes order n squared operations. So it doesn't have as many explicit nested loops as Givens does, but the overall amount of work is still about the same. Okay. All right, so any questions about the householder QR algorithm? And I have code for this on the site. There's a house.m function and a house QR function that implements this. Okay. Now, given a choice, I tend to find generally that between householder and Givens has some key advantages over householder. That because when I was explaining Givens last time, as we go for each column, we would start from the bottom and work our way up. But that wasn't absolutely necessary. There are many ways in which you can order your Givens rotations to zero out the subdiagonal part. But what you could do is you could have Givens rotations affecting two disjoint sets of rows, because each Givens rotation only affects two rows. That lets you apply Givens rotations in parallel if you're working on a parallel computer. So you can get some nice speed up that way. That is not an option with householder. Also, we won't really get into this here, but suppose you want to update your QR factorization. You computed your QR factorization already, and you maybe add or delete a row or column of a matrix, and you don't want to recompute your QR factorization entirely. You want to update it, and you can in these various algorithms for doing this, and they all involve Givens rotations to do the job because you need that pinpoint precision to zero out certain entries. And sad to say, I'm actually having difficulty thinking of a particular advantage of using householder reflections as opposed to Givens rotations. The only reason I can think of off the top of my head is that it might be easier to optimize the code for householder reflections because everything's done in terms of higher level operations, matrix vector multiplications, outer products, operations that tend to be tend to get greater focus when deciding what to optimize. So householder can exploit that kind of optimization better than Givens can. Okay. Now, in the time that we have left, I'm actually going to do a brief return to iterative methods, talk about a couple of iterative methods that make use of where solving a least squares problem is necessary, and that's why we need what I've been talking about the last lecture and a half. So at each iteration, you have some least squares problem to solve, so you have to compute a QR factorization and do all that. And then next week, we will get into the last segment of the course, is my favorite one, algorithms for computing eigenvalues. And then the very last topic will be computing singular values. Okay. Alrighty. So this class of iterative methods, called minimum residual methods, so are somewhat related to conjugate gradient. But conjugate gradient is for symmetric positive definite matrices, and we want to move beyond that now. Okay. So I want to recall one detail from conjugate gradients. Well, really is Lanczos / conjugate gradient. What you're doing is each iterate for solving AX equals B, we're back to dealing with square matrix. Each iterate had this form. It was a linear combination of orthonormal vectors, the columns of this matrix QK, which can be written this way. Where so QK transpose QK is identity. Okay. These vectors, the Q's, form a orthonormal basis for a Krylov subspace. That abbreviated is generated by B. So it's a span of vectors B, AB, A squared B, and so on, up to dimension K. So that was a starting point for conjugate gradient, and we wanted to have these orthonormal vectors be parallel to the residuals, so that the residuals would be orthogonal. So the question now is, can we do this if the matrix A is not symmetric, positive, definite? So the idea is we still want to grow this Krylov subspace basis and use a linear combination of that to get approximate solutions to AX equals B. Here's one thing, so if we focus just on this question, what you'll see is, yes, we can do this, but there's one thing that we can't do. We can't use a three-term recurrence relation. Because that's what we did before. Each of these vectors, the Q's, depended only on the previous two. The trouble is, this inner product that we used for that purpose, B transpose F of A, G of A, B, is not a valid inner product. If A is not symmetric, positive, definite. To be a valid inner product, you have to satisfy, for instance, like the inner product with itself must be a norm squared, and things like that. So those basic properties we don't have. So that's why we don't have that option. We can't generate these vectors as cheaply as we could before. So we'll try something different. And this actually brings about the third approach, which I meant to not cover, but I guess I'm covering it anyway, for computing a QR factorization. And that's called Gram-Schmidt orthogonalization. Okay. So in order to generate these vectors, Q1, Q2, up to Qk. Well, the first one is already determined, so it's B normalized. But once you have that, how do you get all the other ones? So what you do is, for j greater than 1, actually, yeah, for k greater than 1, here's what you do. First, you set vector vk is equal to a times qk, because you're trying to work with polynomials of a times b. So you take the latest vector you generated, which is already a polynomial of a times b, and you just bump that degree up by 1 by multiplying by a again. So this is your starting point, but now what you have to do is orthogonalize vk against the previous vectors you have, q1, q2, up to qk minus 1, or up to qk. Because you're trying to get qk plus 1 in here. Actually, so I can make this k greater than or equal to 1. All right. Now, the way I do that is I have rk is equal to vk minus, and now here's how I do the orthogonalization. I take the inner product of each of the previous q's with vk and multiply that by qj, and I subtract that off. And what you can do is, if you were to take the inner product of this equation with qi, for any index I, what you would find is you would get 0. That one of these terms would cancel out with this. So that makes rk orthogonal to all the previous q's. And then all you have to do now is normalize it to get qk plus 1. Now I should point out that this is actually the exact same thing that happens in the Lanczos algorithm, where we actually compute the same vk and then we orthogonalize against all the previous ones. But because of a being symmetric positive definite in that case, almost all of these terms are equal to 0, except the last two in that case. So in a general case, for general A, we actually do need to compute all of them. Okay. All right. Oh, in fact, in the notes, I do take the inner product of this with qi and show that what you get is 0. Okay. Now, let's take a closer look at this inner product. That is qj transpose, and vk is aqk. So I'm going to introduce some notation. I'm going to call this hjk. And then I'm also going to define this norm to be k plus 1 k. So every time I finish orthogonalizing and then I take the norm to normalize it, that's also one of my h's. Now, if I now rearrange this equation, I get the following. AQK is equal to this sum of HJK QJ plus RK, which is the same as HK plus 1K QK plus 1. So now what I want to do is, this applies for all indices K. So if I put all of those relationships together, then I can express this in matrix form. And I get a similar relationship then to what we saw with Lanczos, deriving conjugate gradient. So I get AQK. So I'm writing a matrix equation where each column of this matrix equation is a previous equation I wrote. And so all those together make a matrix product, QK, HK, plus HK plus 1K, QK, EK transpose. Or what I can do is I can put these two terms together into one product, and that would be capital QK plus 1, HK tilde, where this matrix HK is a collection of all of my little h's that I had before. So H11, H21, actually that should be H1K. In fact, in the notes I have J, so that's a mistake. Whoops, that's 3, 2. It's kind of weird in the notes. I had this correct, but I had J all through here instead of K. And everything down below is 0. So this is called a upper Hessenberg matrix. It's kind of like upper triangular, but there's also an extra subdiagonal below the main diagonal that has non-zero entries. And then, so that's this HK up here. HK tilde is almost the same. I have HK above, and then in the last, I add on one more row that has HK plus 1K in the last position. So it is also upper Hessenberg. Okay. So this process that gives me this matrix capital QK and also the Hessenberg matrix HK that I described over there is Arnoldi iteration. So it is a generalization of Lanczos. So to sum it up, what it does is, so R0 is B, Q1 is R0 normalized, and then we just have this loop. So the Gram-Schmidt process goes in here. I could call this R. Okay. This is HJ plus 1J. Now this is just a repeat of the steps I had on the previous board, but I wanted to condense it all into one algorithm. So our Nolde iteration produces these outputs. We have the vectors Q over columns of capital QJ, and then the Hij, those are the entries of this Hessenberg matrix. So what's happening in this inner loop is Gram-Schmidt orthogonalization. You can think of it as another way of doing a QR factorization, less numerically stable, but the thing is, when it's not clear at the outset exactly what we're orthogonalizing, because we're generating it a vector at a time, unfortunately it's really the only way you can take. But one thing that's key here is that we keep updating Rj and using that for the next inner product. That's important. That helps it become more numerically stable. So technically what I've described is called the modified Gram-Schmidt orthogonalization, as opposed to the classical Gram-Schmidt, where I take this vector, Rj, and I take every inner product with respect to it, and I'm not really updating it. So that's bad. Don't do that. So just that little change makes the algorithm at least more palatable numerically. Okay, so now, as a result of this, I now have this orthonormal basis for my Krylov subspace. But now I need to return to the task at hand, which is, how do I use this to compute approximate solutions of Ax equals b? Because I get my iterates by taking some linear combination of my columns of capital QK, but how do I do that in this case? So, so here's how I can figure that out. Okay. Now, I need to try to avoid a notation quagmire that I've just set myself up for in the notes. Okay. Because what I want is, so the goal now is to find a vector xk of this form to minimize the norm of the residual. So in other words, I'm trying to solve a least squares problem. Now, the thing is, in the notes, I refer to this residual as you might expect, Rk, except I'm already kind of using Rk for something else. And that would not be exactly the same. And worse, this Rk that's residual is parallel to the other Rk. So I'm not going to call this Rk. I do in the notes, but I'm not going to call that here. So I'll need to fix the notes. So I'll substitute this form of the solution in here. And then I take into account the fact that B is equal to Q1 just normalized. Oh, I guess we're done for a test already. Oh, good for that. Okay. Now here, I take advantage of the fact that a 2 norm of a vector is invariant under an orthogonal transformation. So I can multiply all of this by QK transpose. So this becomes E1. And then here I get QK transpose AQK, YK. But that, actually it's QK plus 1. That's what I need to do here. Let's see. Yeah. But this turns out to be HK tilde, the matrix that I have over there, the Hessenberg one. Because that comes about from, where did I write it down? Here, inner products of my Q's with QJ transpose AQK. So this definition is what lets me do that. So now I have 2 norm of norm of B E1 minus HK tilde YK. That is a least squares problem. That can be solved using whatever approaches I covered Tuesday. Whether it's normal equations or QR factorization, preferably using either Givens rotations or Hausdorff reflections. Actually, this should be Givens rotations. And the reason why is HK tilde is a Hessenberg matrix. To compute the QR factorization, all you need to do is eliminate the entries on that subdiagonal. And Householder is going to be way too much work for that. Okay. So using this Arnoldi iteration, and then solving this least squares problem at each iteration, so all I have to do is really incorporate that into the algorithm that I wrote over there. So the result of all this, so in other words, Arnoldi plus solving this least squares problem is a very famous algorithm, iterative method for solving A equals B called GMRes. It stands for the generalized minimum residual method. Okay. So this is probably the best, most often used iterative method for solving unsymmetric large sparse systems. Now, another approach that's often used is biconjugate gradient, which is more closely related to conjugate gradient. But the general sense is that GMRes tends to be more reliable. Biconjugate gradient tends to be faster. Because biconjugate gradient uses a simple free-term recurrence relation to get its vectors that are not orthogonal, as opposed to GMRes that cannot use a free-term recurrence relation to get vectors that are orthogonal. Okay. Because what happens, unfortunately, is this least squares problem keeps growing in size. Now, but you keep adding rows and columns to the matrix, so you could update your QR factorization, like I mentioned earlier, using Gibbs rotations. But that growing expense is a problem. And that's why GMRes is typical to try for several iterations and then restart to avoid having these problems grow too large. Okay. Now, let's see. All right. So any questions about the least squares problem here? One specialization of this, or special case of this, is if A is symmetric, doesn't matter whether it's positive definite or not. Alrighty. If A is symmetric, then GMRes becomes what is called MinRes, which is just the minimum residual method. And the matrix HK becomes the matrix TK that is tridiagonal. And the reason for that is, if A is symmetric, then HK is going to be symmetric also. A symmetric Hessenberg matrix is tridiagonal. And Arnoldi reduces to Lanczos. All right. Okay. So the resulting algorithm is almost the Lanczos algorithm I showed before when deriving conjugate gradient. The difference is, in the Lanczos algorithm I showed earlier that was used to derive conjugate gradient, we just saw the system involving TK, and it was a square invertible system. But in this case, where it's GMRes or MinRes, you're solving a least squares problem with a rectangular matrix, so HK tilde in the GMRes case, or TK tilde that has one row extra in the MinRes case. So you have a system that is overdetermined by one equation, so you must use least squares. So that's the only difference between them. The underlying iteration to generate your Krylov subspace basis is exactly the same. Okay. Alrighty. So I just want to be able to say a little bit about these iterative methods. Missed out on a chance to cover biconjugate gradient, unfortunately. Well, I don't have notes for that. But there you have it. So, but anyway, I'm out of notes. So, okay, so then that's the end for this week, and then we'll pick up with eigenvalues starting next week. Yay. Not that I expect you guys to be enthusiastic about it as I am, but